Surface soil acidity. Some of you have seen it, some of you haven't, some of you have it and don't know it. And so my job is to try to show you why you might have it and what you might do about it. Here we go. All right, so here's a happy little chickpea or a field pea or anything. Nodules are usually within a couple inches of the surface. pH is above 5 and it's pretty happy. But after you've been no-till for, I don't know, certainly 20 years or so, sometimes not that long, and you're putting urea within a couple inches of the soil surface, you can have this develop where you have really low pH. pH of 4.5 is not very good. pH of 5 isn't all that great, but usually you have a higher pH down at greater depths. But anyway, that surface, really low pH, and a legume trying to grow in a situation like that isn't going to do very well. It's not going to nodulate hardly at all. And other crops have a really hard time growing with that low a pH. So, okay, that's interesting and scary. So where in the world did all that come from? Well, acidity in the soil comes from a variety of sources, and even crops just growing squirt acid out of their roots as just part of their metabolism. But the greatest contribution to our acidity, especially this systematic, structured, stratified acidity, comes from ammonia that's in the soil. And that ammonia could come from fertilizer, it could come from manure, it really doesn't care. When ammonia is put in the soil, it's in association with water, and then there's nitrification bacteria everywhere. I mean, it's in all of our soils. There are bacteria that take ammonium, which is this here, and it transforms it into nitrate. And so instead of NH4, you got NO3, and you split the water, and this hydrogen plus some of that water goes into this. And that is what we measure when we measure pH. The lower the pH, the more of the hydrogen ions we have in solution and activity. And in no-till, we see it first. Conventional till people are also going to have this problem as we go through time, but they mix their soil. And so the effect of the gradual decrease in pH isn't quite as noticeable as in no-till because they mix it. In no-till, most of the nitrogen is applied at or near the soil surface. Our main fertilizer now is urea, and so that's usually put within a couple inches of the soil surface. Even a lot of our ammonia is put down maybe 4 inches, 5 inches or so, and so it kind of taps in toward the surface as well. And almost all of it is nitrified into nitrate, and all of it produces acidity. If your soils have free lime, the change in pH is relatively slow. If you don't have free lime, the change in pH is relatively fast. So the lime acts as a buffering, and I'll show you that in a minute. All right. So having low pH releases a couple of nasty things. There's tremendous amounts of aluminum in our soil because that's what the clays are made out of. They're made out of silicon oxide and aluminum hydroxide. And as long as the pH is, 5.2, 5.3, hardly any aluminum at all is in the soil solution. But when we start to get pHs less than 5, the aluminum from the edges of the clay starts to become soluble. When it frees up, it splits the water itself, attaches to hydroxide ions, the other half of the water, and that frees up more hydrogen ions and acidifies the soil even more. The aluminum itself becomes toxic to the plant, starts to become toxic when you start to get soil values of around 25 part per million or greater. The aluminum can tie up phosphate, and so that's kind of a problem, but it also plugs up, it's taken up by the plants, and it plugs up the plumbing. That's a good word for it. It plugs up the plumbing in the roots, and the roots become abnormally shaped. The root mass is really reduced. The plant really begins to suffer and suffers drought stress way earlier than it should have. Also, manganese, which is present in all of our soils. We don't have a soil in the state that has a manganese deficiency. That becomes really soluble, and that toxicity has now been identified in North Dakota in some of these low pH soils. So this is a picture of a wheat suffering from aluminum toxicity in the southwest part of the state. And you have some areas up there too that are also suffering. So the stand isn't very good, and the wheat that's there isn't doing very good either. This is aluminum toxicity in canola. The height is a little bit, it tends to make you think that maybe this isn't a big deal, but notice the number of leaves here. We have several more leaves here than here. The stem is just kind of elongated. The fine roots along the roots here, there's a lot less here than there is here. So this has been limed, pH of 5.7. The aluminum concentration is background levels, but here there's no lime, pH of 4.4, and you have over 60 ppm of aluminum. So manganese can also accumulate in the plants, and we've seen it in canola more than anything else, but I assume that it's also in others. Here, with a pH of 4.4, the manganese tissue test was almost 1600 ppm, where the normal range is 16 to 100. When you have this kind of accumulation of metals in the plant, it really messes up the plant's metabolism, and so the utilization of iron and other micronutrients is greatly reduced. So how do you find these areas? Some of you have these and don't even know it. And the reason that you do is either number one, you don't soil test, or number two, you do soil test, but you use a composite test. And a composite test just, is your best guess. Most typical soil, number of different soil cores going into a bucket, and you all mix it up. Only takes maybe 1-2 cores that have free lime in it to screw the whole pH up for the entire field. So you really have to zone sample the field, hilltops, slopes, depressional areas. And then of course, if you have a problem spot, definitely take that. Where composite samplers never take anything unusual. When you start to zone sample, unusual is important, because sometimes these unusual areas can make up, I don't know, 10-20% of the whole field. So zone sample, and then when you sample, it shows here, this is, I appreciate Chris Augustine, who's the director of Dickinson and my former PhD student, gave me these slides. I really suggest a 0 to 2 and then 2 to 6, as opposed to 0 to 3. But anyway, the big thing is, in the past, we've just recommended a 0 to 6 inch core, but that's not good enough if you're no-till and you have stratified acidity. So you need to break that surface 6-inch core up into a 0 to 2 inch depth and a 2 to 4 inch depth to try to figure out how bad, if it's bad, the acidity is going to be in some of these areas. In 1996, it wasn't pH that was driving me, it was copper. But anyway, I went to every county in the state, went to 3 fields within every county in the state. And within each field, I did a hilltop, a depressional area, and a slope in between. And I have part of the data set for it is the soil pH from North Dakota. And here you are, right in here. And you tend to be a little bit lower in pH than your surroundings, but at this stage you're slightly acidic, but not horrible. But that was 25 years ago. So there's a lot of crop and a lot of nitrogen been applied since. But even at that stage, we had pHs in some areas in the survey that were down as low as 4.9, and a lot of them that were in the 5s. So this has been slowly coming on for a long time. So intensive crop growth, but certainly the application of any ammonia-based fertilizer, including manure, results in that surface soil acidification. And so the remedy is what we call liming, and that's the application of any amendment that reacts with the hydrogen ions to form CO2 and water. In conventional till systems, the liming material is incorporated in the soil during the tillage passes, and then I'll give you my philosophy on surface application here in a little bit. This is not a new concept to go from not applying any lime to all of a sudden seeing a crisis develop. Back in the late 1800s, early 1900s, Southern Illinois, my original home state, is the Southern Illinois was being depopulated because a lot of the fields, many fields, thousands and thousands of acres, were being abandoned because you couldn't grow a crop there anymore. And people didn't really understand pH back then. But then in the early 1900s, there was an effort to try to figure out what was going on. And luckily for Illinois, most of the state, the soil overlies huge limestone deposits that go from Chicago a couple hundred miles south. And so this circular came out, Extension Experiment Station, on wheat from stones. So here we are 110 years later, and we're talking about wheat from stones. So this is a limestone quarry in Illinois. I came from near Joliet, and really the limestone really came within just a few feet of the surface. It was that close. And in other parts of the state, you maybe have to go down 50, 60 feet or so, but there's limestone everywhere. So lucky for them, not quite so lucky for us. So our sources of limestone include perhaps water treatment plant lime. They use very finely ground limestone in their treatment process in order to flocculate all of the impurities, and they settle out at the bottom of the pond, and then they're dredged out and usually taken to a landfill, but you could use them to good use by applying those on your field. Come on. Come on, come on, come on. All right, but then you also have the Sidney, Montana sugar beet plant. And there's large piles of sugar beet waste lime outside the Sidney, Montana sugar beet plant. And they use very finely ground lime brought in railroad cars, and that goes into the sugar stream and helps to flocculate all of the sediments, and they settle out to the bottom, and the sugar stream is more purified, and it goes into its final stages of processing, and then the sugar beet waste lime is waste lime. So it's also available to you, and some of you are pretty close to the source. Oops. All right, so I would say, there isn't anybody west of the Red River Valley that's really set up to do this right now. And so you're really at the cusp of a logistic thing, because this isn't something that you're going to put 100 pounds of pellet lime on and you're going to cure it. It's not going to be like that. You're going to have to put on probably a couple ton, maybe more than a couple ton. Depends on if you till it or not, and it would break you to use pellet lime to do something like that. So the material, hopefully it's free or close to it, and it's going to be hauled out in the field and dumped, and then it's going to be loaded up onto a fertilizer spreader. This dates me a little bit. That's the 7th Terragator that was ever produced out of Jackson, Minnesota. Our company had it, and this picture is, gosh, over 40 years old. So then you load it up into a spinner spreader, not a pneumatic spreader, God forbid, and then it's spread onto the field. So it's a logistic thing. So you have to have trucks to haul it in. You got to have the source. Then your trucks haul it in. And then you have to load it up into a suitable spreader. And usually the sides have to be fairly steep and maybe graphite lined, because this stuff has water in it. The water treatment plant lime, the Sidney, Montana treatment lime, all of that has a water component in it. And so it's not going to be nice and flowable. So There's people in the Red River Valley that are set up to do this, and they spread beet lime on beet fields all the time because the beet lime almost eliminates any risk for Aphanomyces root rot in sugar beet. So it's for the last decade or so, a lot of the piles around the Red River Valley beet plants have disappeared because farmers are putting on 5, 10, up to 20 ton of lime to get rid of Aphanomyces. All right, so this number right here, the calcium carbonate equivalent, is what's going to tell you how much lime you really have to apply. 100% would be 100% calcitic lime that's fairly dry and fairly fine in size. All of your water-derived lime sources are going to be very fine. So that's not going to be a problem. It's the moisture content within them that is going to make the CCE lower. So if your rate of limestone coming out of Sydney is recommending 2 ton of lime, it means 2 ton of 100% CCE lime. So it's really going to be 3.25 ton of Sydney, Montana lime in order to satisfy that recommendation. So this is some work by Chris Augustine. Chris Augustine is working on this. He did it while he was working at Minot. Now he's down at Dickinson. Ryan Beto is also working on it down at Dickinson. And Jim Stricka is going to be speaking right after me, has started a project in Williston. And I think they'll probably work together on this. This is some early data that Chris has of no lime applied. Let me see if it's, yeah, there we go. Of no sugar beet lime applied, and the pHs of those soils are anywhere from 4.5 to 4.3. And this is with 2 ton per acre of sugar beet lime, and it's increased the pH somewhere around a half a point or so. And then 4 tons per acre of sugar beet lime, and they're kind of in the range where they want to be. So this is a logistical thing. And so trucks and loading and spreading, and I would recommend doing it in the fall of the year because you're going to be going back and forth to the piles many times. And imagine your spring compaction doing something like that. I would certainly not recommend that. So I would do it, say, after a wheat harvest, after an early season legume harvest, something like that, where you had a couple months to get everything in a row and get it spread before winter comes. This is the effect it has on the field. This is a Minot study, and this is worked into the soil around 6 inches or so. But this is what it looks like right on the surface before you go in there with a chisel plow. This is what it looks like with 2 ton an acre. This is 4 ton an acre here in the back, and then 8 ton an acre here in the middle. But you're probably going to be working with these 2 to 4 ton rates is what I'm going to guess, if it's not too horrible. So we're right at the very beginning of doing this work. Ryan and Jim and Chris are all at the very beginning. Other people have done surface applied lime work before and have had pretty good success and really good yield increases with doing that. Whether that's going to be the case in North Dakota, we're not sure yet. Our friends and colleagues in Montana nearly insist that you have to work it into the ground, and I really kind of hope that we don't have to do that. Maybe we've hit this early enough, at least in the urea fields where the stratification is really at the surface. I was a little bit disappointed last night when Ryan Beto sent me some data from Dickinson where a person had been putting on an anhydrous ammonia and the pH was 4.3 all the way down to 6 inches. And he hasn't raised a crop on it yet. And so I'm really curious whether a surface lime would help him out as much as it could with doing that. But gosh, I'm really reluctant to break up no-till ground. because of the erosion problems and other issues. So anyway, my hope, what I think, and what I've read in other papers in other states is that surface application can help quite a little bit, and it can raise the pH in the top couple inches up to levels where legumes can be happy again, and wheat and other crops can be happy again. So we'll see if that can happen. But in the back of my mind, the erosion is just an ever-lurking danger to continued soil productivity, and I think all of you that are no-till understand that. Continuous no-till has a nutrient efficiency benefit, and deeper passes, deeper than 3 inches, can eliminate that no-till benefit for at least 5 years. So this is what I think would happen if you went in with a chisel plow. And if you did go in with something like that, I would just do straight shanks. I wouldn't do curve. I would leave as much residue as possible up at the top. But when you do that, you're going to destroy all the food or all the housing that those microbes have. And so it's going to take them a while to recover. The first year after that, you're going to get a burst of mineralization because of oxygen being introduced into the soil, into those little cracks and crevices. And so you'll have some nitrogen release. And so you may still keep the long-term no-till end credit that first year. But I think after that, and this is just me thinking, this is all new for me, is that second, third, fourth, fifth year or so, you may not be able to take that nitrogen credit because you're not going to be releasing any nitrogen from excess nitrogen from mineralization. And you're going to be building up that microorganism population that's helping you reduce your rate of N. And so, but if the alternative is that you're not going to grow anything because the pH is so dang low, you really just don't have a choice. All right, so here are the steps to remediate the surface soil pH. Well, first of all, you really need to find out if that's what's going on or not. You need to zone sample the field, and within that zone, you need to sample for pH at the 0 to 2 inch depth and the 2 to 6 inch depth. You need to have the lab run pH or buffer pH or both on both depths. You need to lime up your lime source. You need to schedule the application, do it in the fall to avoid compaction, and to have it react a little bit before you seed in the spring. You have to apply before freeze up because, again, this stuff has water in it and it's going to be unspreadable if those temperatures get into the teens. Pellet lime is just too expensive to apply it at ton per acre rates, and it's no more efficient than any other kind of lime, so don't let anybody tell you it is. Oh, okay. So one last thing, and I don't have a slide on this. I just sent Jim Sturicka and Claire Keene a publication from Washington State on the use of soil probe sensors. There's a number of pretty cheap and pretty accurate soil sensors that are out there. And so when you take a core out of the ground, you can actually find out the stratification within that core just with that probe without even sending it into the lab, and be pretty accurate. And so, you can choose your depths. You can check the 1 inch depth, you can check the 2 inch depth, you can check it down to 3 or 4, you can check whatever you want. And I've talked to a consultant out in Washington State where they've had this problem apparently for 30 years. And it's one of the best kept secrets in modern science. But they use it regularly. And so I've sent that to Jim and to Claire. So if you'd like to have a copy of it, I'm sure they would be happy to share that with you. So with that, I'm done.
Great, thank you, Dave. Any questions from the audience here? Any questions from anyone online? Oh, I see one popped up.
Yeah, I'll read it if it's all right. So the question is there a difference between urea and anhydrous ammonia in acidification per unit of N or pound of N? And that answer is no, there's no difference between those two. The N source where there is a difference is ammonium sulfate. It's not quite twice, but it's certainly more acidifying than urea or anhydrous ammonia.
Okay, one last chance for questions from the room. Yep.
Do you think with the ammonium sulfate being more acidifying, are we at greater risk where we're producing canola?
Yeah, so the question was that if since ammonium sulfate is more acidifying than urea or anhydrous ammonia, are we more at risk when we grow canola? A tad more, but a lot of your spring wheat growers are also using some sulfur as well. But the situation where it would really make a huge difference was if for some reason the cost of nitrogen and ammonium sulfate was 20 cents and the cost was 40 cents, and a grower was tempted to go ahead and put all 150 pounds of nitrogen on as ammonium sulfate, and that would make a big difference. But certainly the greater acidification is not zero between the canola rotation and other crop rotations, but it's not that much different.
One more. Sorry, one more from the audience.
This is for a sulfur source then, if ammonium sulfate is not good.
Did you hear that, Dave?
Yeah, so the question was, what do you use as a sulfur source if you don't use ammonium sulfate? And I think I would still use ammonium sulfate. It's that's not going to be the breaking point whether you have acidification or not. You're going to have to lime no matter what you do. So you may give up ammonium sulfate and go to twice the rate of granular gypsum, but you're still going to be able to. You're still going to have to lime, and so I think you got to wrap your head around that more than you do your sulfur source.
Dave, I'll let you pick maybe one question out of the chat to answer. I see two there, and then we'll need to move on to Jim.
Yeah, okay, well, they're both real quick. Any updates on my nitrogen tool? And the answer is no. It's pretty stable. So, and then next, approximately how much lime would it take to fix a 4.0 saline seep? And you did not add, there's no amendment on Earth, there's no amendment in the known universe that you can apply on a saline seep and get rid of a saline seep. So that's easy. So it'll never fix it.
Right, and I'll just say saline seep management's all about water management, and if you would like to have that conversation, please contact me or Jim or catch me after we're done. Thank you very much, Dave. We appreciate you joining us here for the Wheat Show.